скажу, что нас объединяет. Объединяет нас то, что, я уже это отмечал, что в свое время на работу Степана Прокофьевича Тимошенко, который остался в то время без работы и начал работать в политехническом институте, соответственно, отзыв написал Иван Григорьевич Бубнов, создатель первого в стране курса строительной механики корабля. И тот абзац, который он написал, без единой формулы, он вошел в историю как предложение метод Бубнова. Потом, спустя несколько лет, он заведовал у нас кафедрой строительной механики и теории упругости. Борис Григорьевич Галеркин независимо предложил метод решения дифференциальных уравнений, известный как метод Галеркина. Во всем мире это известно как метод Бубнова-Галеркина. Правда, во вступительном слове или в ответном слове профессор Оньяте упоминал еще и академика Петрова. Это московский академик, это гидродинамика и так далее. Метод Бубнова-Галеркина. Тимошенко вместе с Степаном Прокофьевичем, с Абрамом Федоровичем Йоффе создал физико-механический факультет. Они одноклассниками были. Но Тимошенко в 18 году эмигрировал и создал всю прикладную механику в Соединенных Штатах. А Абрам Федорович Йоффе, создав и возглавляя многие годы физико-механический факультет, создал Советскую школу физики. Вот это я хотел бы в предварении, значит, лекции профессора Эухенио Оньяте на актуальную для нас тему, чем мы с вами занимаемся, вот сказать несколько слов. Профессор, you are welcome.
Большое спасибо, профессор Боровков. It is a great pleasure for me to be here today and share with you some ideas about my personal view of the evolution of this field that we call numerical methods in engineering, which is nothing else how predictive methods, the methods that we learn when we study mechanics. I prefer to. Do they need it? No se oye? Okay, this is better. Okay. So anyway, so where are we coming from, and where we are, and where I think we are going, and of course, this is only a view from my side, and my side is the Technical University of Catalonia in Barcelona, an institution which is only 50 years old, and where we founded this organization that I will tell you in a minute, some 35 years back. Well, here is Barcelona. It shares with St. Petersburg that we are next to the sea, perhaps a different climate. Sometimes we also have snow. And this is a view of the harbor, the view of some of the spots of the city some of you might have visited. It's a place I recommend you to visit. And now that I am a member of this community, I invite you as a colleague. And we created this organization in Barcelona 35 years back with the aim of being a transverse organization that will take the knowledge that we learn in my case, civil engineering, to other fields. Now this center has expanded. We have some 300 researchers from many different fields. And we are located in several places in Barcelona. We don't have a Cibne tower. We have several Cibne buildings. And this is our new building now, next to my office. And in all our buildings, we have a penthouse where you can see the sea. This is what you see. Well, at the end, you cannot see. Oh, this is the sea. This is the Mediterranean Sea. And as I mentioned, we cover many different fields in mechanics. I'm not going to enter into the details of what we do, but perhaps I will tell you that we have been selected as a National Center for Excellence, and these are the keywords that we use to be selected. We are committed to do research in construction and transport. And transport for us means aeronautics, means naval, means road transport, railway transport, environment, energy, and security, very important issues. And of course, the manufacturing sector and anything to do with the new materials, biomaterials, electric-based materials, and metamaterials, materials with unique properties that you manufacture using additive manufacturing techniques. We are a famous center, but we are not the most famous organization in the city. And we know that, and we have to acknowledge this. And so this brings us down to earth. What are the important matters in Barcelona? And we have been evolving from the importance of this letter C, computations, to this tetrahedra. A tetrahedra that is a finite element, as you know, with 4 nodes. Every node is connected. And now we face the solution of every triple P, a product, a process, a problem, is a combination of the C, of the D, and of the M. M are devices. And this has allowed us to enter in new fields, like, for instance, social science, where there is a lot of D, and maybe not so much computations. And I think that we have evolved from being a center only focusing in the computational method to an integrator. And anything, for instance, my mobile phone, your mobile phone is an example of this integration. And also, we invented this circle some 20 years back to explain that we are not competing with the university. We are part of the university. We are owned by the university. I am a professor at the university. I am in this interface here. But our role is to take any idea that originates in the university, and as a plant, as a baby, or like the water flows, it needs to go through different phases. And to reach success, you have to really success in the independent phases. A PhD is the result of the research at the university. But a PhD sometimes is not used, is repeated because the student goes. So anyway, you can see that there is a need to explain that there is a role for these institutes, as you have here. And this is perhaps not the end of the story, it's half of the story. Then the companies do the rest of the work. And then the market, society, is the final ending. And the innovation here is that we have set up this link of cooperation at the university side, and also have created our own spin-off companies that help us in this cycle of ideas. Now coming a little bit more technical, and I'm going to perhaps abuse of your patience, and I will tell you some very basic things, and perhaps some other things that might be more interesting of those of you who are experts, but I didn't know what was the expertise of the audience in general. So we used to say that there is a need for a transverse education that will help us to identify the commonalities between structure analysis, fluid dynamics, and processes that use fluids and structures, like manufacturing processes. And the key word is predictive quantification. And to quantify means to produce numbers, we need to know about the problem. It's very important to know about the physics of a mechanical problem, which is different from another one. We need to express this in mathematical equations, and we need to solve these equations. And in fact, everything comes with our perception of reality. We can produce mathematical models. And the numerical methods is a tool to apply what we call computational models. So first is the mathematical model, then is the computational model, and then comes the numerical methods to solve it. And this sentence impressed me when I read it. This was referring to models in economy, but I borrow it because we are criticized all the time that our methods are not perfect. Perhaps we should say all computational methods are imperfect. They are not perfect, but some are useful. And this is, we have to admit that. And this is what engineers have been doing all their life from history, making use of the available knowledge to produce useful things for humanity. About reality, this is very important because now we are talking about different kinds of reality altogether. For instance, what is the scale of interest? Are we talking about the subatomic scale where we have numerical methods, or are we talking at the aircraft scale? So for each of these scales, the methods are different and the objectives are different. The mathematical models are different. So this is very important, and one cannot be an expert in all the scales. Even in multi-scales means many things, because when we talk multi-scale in environment, macro scale is the basin, is the territory. Micro scale is 100 meters near a bridge, a mesoscale, excuse me. And micro scale means near the bridge. So we use these words in a different mode depending on the problem. And this is simply meaning that there are different methods for every scale. Right? This is a challenge. Already we are talking here about the future more than the past. Now, this is what we teach to our students at the MSc level, even to our postgraduate students when they start, is how to model mathematically a problem. And this is well known for all of us, but maybe 3 minutes talking about it, is that everything comes from balance law, equilibrium laws, Newton law. What comes in goes out, or sum of forces equals 0. And this gives us the differential equations. Differential equations which are satisfying a domain with the boundary conditions. And this is the simplest differential equation with only one scalar, it's the temperature. But in general, they can be cast in this form, a set of differential equations with the boundary conditions that we need to solve. And for years, for centuries, people have been trying to solve them analytically. And only in the last 100 years, we are learning that, or we have been using humans other tools to get numbers, not the Pythagorean expression of the solution for every parameter, but the actual numbers, the need for numerical methods. And it's very interesting to classify 3 different types of problems. First, what we call static problems. Time is not involved in the equations. And you can read here the classes of problems that includes these simple equations. Structural mechanics and many other problems that are governed by this set of differential equations. When you introduce time, you have a class of problems which is all fluid mechanics problems that are governed by this type of kind of parabolic equations with only the first derivative of the unknown, the velocity is the unknown. So this is a second set of big problems. And the third class of problems goes back again to structural mechanics or acoustics, which is the second order dynamic problems. Okay? Each of these classes of problems requires a different strategy at the analytical level and at the numerical level. I think with these 3 classes of problems, we cover 90% or even more of the problems in mechanics. And when I talk mechanics, I mean physics in general and engineering. And of course, the name of Timoshenko comes here because he spent his life solving analytically the first class of problems, a little bit the third, dynamic equations. I just mentioned during my small gratitude speech during this honorary doctorate that when I was 19, I was introduced to Timoshenko in the books of elasticity and strength of materials. And then I learned, we all have learned, and still we are learning about the expression that he derived, solving analytically those equations. He belongs to the classes of engineers who really looked to the equation, got solutions, and these solutions were applied in practice. But not only Timoshenko. Last Friday, I took these pictures at home. These are books from Russian scientists that I used when I was a student. Most of them were published in Spanish by Mir publishers, this editor publishing house from Soviet Union in those days. But we actually, I have these books at home. These are my collection of books. And I was very proud to really recognize, acknowledge that my background comes from this cultural heritage from your country. And of course, this is not a course on numerical methods. I cannot actually go step by step, revising all the numerical methods. I'm going to talk a little bit about final elements, which is the recent past and the present, and about some new methods that I think is the future. Okay, and all comes from the so-called variational forms. You know that most numerical methods are based on the discretization of the domain and using the properties of the integral that they can be added through computed by summing the contribution from different domains. And this is the so-called weighted residual form. You're familiar with this. You multiply the governing equations by weighting functions, and then you assume that this solution of this integral form for any arbitrary function is equivalent to the solution of the first equations. This is the basis of all numerical methods, including finite difference could be casted in this form as well. And here comes the name of a distinguished academic of this university, Galerkin, together with Ritz and Bufnov, also from this university, and Petrov, also from this country, developed classes of different methods applied to this general framework of weighted residuals. And from this, in fact, this is a personal note, I'm sorry, but I'm very proud to carry the name of Galerkin in my curriculum, because I was awarded the Galerkin Medal from the European Association for Computational Methods only this September. And I got it, so this is a double privilege for me for being here today. I'm not going to, I promise, I promise, when you promise something, you know that it's not going to be true, but almost zero equations. This is almost zero equation lecture. But I have to mention that Galerkin, as you know, introduced symmetry in the system of equations that we are solving by, you know, in finite elements, you use these small domains with which you interpolate your analysis domain, and you use these so-called shape functions n. So Galerkin choose for the weighting functions the same approximation functions, and this introduce symmetry in the solution that you are solving. So you are solving a problem of structural mechanics. This K matrix is symmetric, and this is the Galerkin, or Bufnov-Galerkin. In fact, we should say more rigorous saying the Bufnov-Galerkin form. Okay, and the beauty of finite elements is that these equations, the system of equations you form by assembling, by using the information from the individual elements. So this is something which comes from discrete systems, as you know. But an important matter that I was not aware when I was a student, and I learned later, is the link of the Galerkin form with the principle of virtual work. Let me just in case some of you are not aware, let me just say two words. Look for a problem in structural mechanics, a simple problem. You have displacements, forces in the boundary, in the body, you have the strains, you have the stresses, you have the constitutive form. This will be the basis for obtaining the differential equations, which are obtained by equilibrium. Sum of forces equals 0 in the statics. And this gives you the equilibrium equations in the body and in the boundary. And this is the equations that Timoshenko solved, okay, expressed in terms of displacements. When we apply weighted residuals, we multiply these by weighting functions. Now, these weighting functions are what we call virtual displacement, and then you obtain the weak form, the integrating by parts. What you obtain is the principle of virtual work. So the principle of virtual work is nothing than the Galerkin form of the differential equations in mechanics. But the beauty is that when I lecture in my course, final year students in civil engineering, and I teach finite elements, I don't start with equations, and I don't start with Galerkin. In fact, I don't know about Galerkin. I start with this expression. It's equivalent. It's equivalent. And the beauty is that also can be interpreted in terms of work. The work of the external forces over any arbitrary displacement is the work of the stresses in equilibrium with the actual forces versus with the work with induced by the virtual strains. So from this moment on, I don't say we can forget about the past, but we can start from this expression. And this expression is independent of how we obtain the stresses. So it applies to any nonlinear material. It's also independent of the size of the displacement. So it applies to any problems of a small or large displacement. It also applies to dynamics. So it's a universal form from which I can derive any approximation method. And also, if you look back and you interpret the internal work and the external work as variation of the actual work, you see here by this simple manipulation, you derive the principle of minimum potential energy. Simply, look, it's expressed in the transparencies. I'm looking to the screen. You see, I'm not going to detail. But what happens is that all the energy theorems that I study, Castigliano, Menabrea, when I was a student, I was using energy theorems. When I was postgraduate at Swansea University, I learned that this is a consequence of the virtual work. And in fact, the energy is very difficult to compute for nonlinear systems. But you don't need the energy. You only need the variation of the energy. And the variation of the energy is the principle of virtual work. And you can use it for any problem in mechanics. In fact, this is a book each of us or every researcher should have, energy theorems in structural mechanics. This is prior to finite elements, a few years prior. But in this series of papers collected in a journal in 1954, Argyris applied this concept of virtual work and complementary virtual work to derive equations to solve practical problems in the British aeronautic industry. These are pictures taken from those papers. From this, he obtains force displacement relationship from energy theorems. Okay, but what happens? Soon it was realized that if you use this discretization in triangles and you express the approximation of the unknown within every triangle and they use virtual work, naturally you derive a system of equations. So you go from energy equal energy, joules equal joules from the principle of virtual work to a set of equations, forces equal forces. And this is the expression that you see in the last row, is the expression for the general nonlinear problem. And then if you assume that the problem is elastic, and you introduce the elastic constitutive equation, then you have the force, the standard force equal stiffness matrix times the displacements. So you see this. I found fascinating this historical development with time, because now we have a systematic way to apply any discretization method using virtual work. But in case we have a new equation, we always have Galerkin, we always have weighted residuals to apply and to obtain perhaps new variational forms in the future. So this is what we are. And you see, we have a bridge, we divide it in finite elements, and we obtain the solution. Is this new? Well, it's new. We can see that it's not so new. This is what Archimedes did to compute the pi number. He used an element, the segment. He used a discretization, the number of segments, inscribe or circumscribe, and he obtained bounds for pi. By the way, pi is a number with infinite digits. It's a number you cannot compute exactly. So this, I think this was the first idea of approximation using this concept of discretization and subdivision. This was 300 years before Christ. And it took 7 centuries to find this reference of a Chinese, but 7 centuries, no 7 years, that he used the concept of areas to obtain bounds for pi. So, I found this interesting also to put it as a kind of historical background of what we're doing, historical perspective. And in fact, before I learned finite elements, I knew how to compute hydraulic networks. I knew how to compute an electrical network. I knew how to compute a structure using matrix methods. And I knew that I could use the matrix, the information from an element, use Kirchhoff theory, Kirchhoff theorem, sum of fluxes equal the external flux, or sum of forces equal to the force, and go from the element to the structure. And this is what we do with finite elements. In finite elements, we have more complex systems, but you have the same, precisely, this is a copy of the past transparency. But now, the element we create, we don't have a pipe, we don't have an electrical network, we don't have a bar. We invent the element, but we follow the same trend. Look at the element, look to the balance of the element, use a general balance law, and get a general system of equations. Okay, so having understood that, we have made a lot of progress. The method can be applied, and this is some colorful reference after those equations of how we apply the method in structural mechanics, but I could use many others. In fact, also how do we compute the strength of mechanical elements, and how we apply this to the many engineering sector in the mechanical manufacturing sector. Just three references if you want to have a collection of these pictures. By the way, I will be happy to provide this lecture to Professor Borovkov later. If you are interested, you can have it all. We have to acknowledge the work of Courant. Courant made a reference to discretization of a domain into triangles in 1940. But the first paper which is acknowledged to be the predecessor of the finite element is in 1956. This Turner, Clough, Martin, and Top. But the name of finite elements was not used only until 1960 by Clough. Okay, so perhaps some others are missing, and this is like a work for the historian, so to look into the archive of history. Yeah? But this is how I've been taught. But everything in my life came from a different place, from Swansea. Swansea is a beautiful spot in Wales, beautiful beaches, amazing place. Weather is okay, simply okay. But then I found this man, Professor Sienkiewicz, Olgi Sienkiewicz. He was there at the right time. In the 1960s, he was a clever guy. He came from relaxation method, from finite differences. He was from Imperial College, went to the United States. He came to Swansea, and then he saw the trend, and then he jumped into the trend. And then I was happy to be his student, and this is me. You won't believe it, but this is me. You can see that. Guess who is me there in the picture? In the middle is Professor Sienkiewicz. When I was graduated in 1978. And then when he retired, he came to Barcelona for almost 20 years. And he actually put us in the map because everybody came to see him. This is a celebration of his 70th birthday in 1991. This is Professor Sienkiewicz and myself with many colleagues, and I found the power of having a distinguished person, actually, you can make a progress of 100 years, You could not get this yourself in your life. So we took this advantage, and many other persons came, like this is Professor Taylor, Bob Taylor, a co-author with he was almost his personal assistant. He was he's still alive, he's almost 90 now, in Berkeley. And this is the Professor Sienkiewicz just before he died. This was, he died in 2009, and this one he turned 80, and this is the picture we have in the Sienkiewicz room, where we have our seminar room. Is called the Sienkiewicz room, and this was before he died. You see, he was keeping a very, I would say, perfect face of vitality. These are the three caballeros of the finite elements: Argyris, Clough, and Sienkiewicz. Not that Argyris and Sienkiewicz had a good relationship, not bad, but they work in independent routes. So I think this is a good picture. So we have a method that can be applied to any problem where we need to find out stresses, strains, resistance, or maybe other things. In this company is making advertising the value of the methods they use to protect the texture of the skin, with finite elements. In the early days, finite elements were applied to dams, dam engineering. Okay, dams. well, this is an early paper, 1970, a dam in China. Now, the use in dams is a regular practice. This is just one example of a dam in Spain. This is exercises that our students do to compute, to apply the methods that we teach them. So dam engineering is a reference for the past, and also for the present. That's as a teaching scheme. And also, this is, I said that Fanadam is the only method that allows you to compute this building. This building, the facade is the resistant member because there are no columns inside. This is a building in Barcelona. And you can see that there are no methods that you can apply here with so many windows, that the finite element method. And this was applied by a company in Barcelona with our help. You see, there are no columns. All the roofs, all the slabs hang from the facade, who is the resistance building. It's called the Akbar Tower in Barcelona. But of course, we are not only interested in the design of buildings. We are interested in to know the safety, or how to protect the buildings, or how to what is called to enhance the properties of the retrofitting some of the buildings. We're interested to see when cracks start, which is the failure load, and for that we need nonlinear analysis. And here comes the concept of virtual lab. Virtual lab is a lab that you build in the computer, and with that you break the structures, and so you compare with some experiments. But we have created this virtual lab that we apply, and we can, and with that, we can predict, push this structure and see when it fails, and we can see how we can reinforce some parts and get higher loads and improve the behavior. And we have applied this concept to see what is called forensic engineering. This building had many cracks. Why? Well, we take the building, we discretize, we increase the weight of the floor, we see when it fails, we see the cracks, and we compare this with existing cracks. This is called forensic engineering. Forensic engineering requires nonlinear mechanics problems. And this is very much applied now in the nuclear sector in Spain. We are still today involved in the study of the safety, predictive, projected safety of the nuclear plants in Spain. There is a big debate in the world, and we are guessing that the nuclear power is going to stay, for many reasons. But what we are doing here is we see how what will be the failure load of this containment building when, for instance, there is an increase of pressure inside. So increase the pressure until we obtain the failure load. And the colors are nice, but this is the main curve. Curve which shows that as you increase the pressure, then you get damage until you have damage, the global damage reaches 1, and this is gives you the failure pressure. And this is the comparison between axisymmetric and three-dimensional analysis. Okay, so this is what we are doing now with a number of power plants in Spain. But also in historical buildings, this is applied. Of course, here there is I would say the financial interest or the social interest is less important, but in Italy there is a big interest. There is a congress of this field that we have been organizing over the years. And for instance, I was paid here for this. The reward we got is that I walk in the roof of the basilica, and I could see that for instance, these towers are fake. They are wood and copper, and the actual domes are of stones, and you can see them here. And here is the same. We increase the weight. Damage produces the colors. They know damage until you reach a failure, and you can compute the cracks, and you can compute the failure load. So another case for which we obtained the City of Barcelona award. For these color pictures, we were given an award. And of course, we didn't know anything about the materials, so I think this was a non-deserved award, but we took it in a case. And you can see the concept of failure of an historical building. You increase the pressure, you increase the weight, and as you increase the weight, you can see that you actually destroy, you see, the structure. It's the virtual failure lab. You can apply to real structures or to mechanical parts. This was the failure lab applied to compute the failure, the number of cycles for failure of this pump casing. that we computed. It's the same concept. Or to compute here, for instance, well, I will not put the video, to compute the failure load of this composite that you can compare with experiments. Now, let me move to fluid mechanics. This is an area of much interest for many reasons, not only in aerospace, for the design of cars or any element which is exposed to wind, like this the big telescope, or for instance for the naval sector, for the marine sector, with many applications. For instance, in marine engineering, and we have set up a big group in this field, we have introduced the concept of a virtual towing tank. A virtual towing tank is a space where you put your ship and you tow it and you compute the resistance. And this is an example of how in this virtual tank you have to fill it with elements, then you have to put your ship and then push it. And here is a video that shows you how this is like Moses, that fills the sea with, it reminds me to that. You see, you fill the sea with tetrahedra, and then you put your ship, and then you have to pull it. This brings us the problem of mesh generation, controlling geometry, which are very important parts of the analysis. This is an American Cup boat with with an underwater, and then the importance of visualizing the results. Okay? Some people say that CFD is color fluid dynamics. Well, it is true that colors are very important, but numbers are also very important. So, in fact, numbers are more important. So this is just an example of how this is applied. When you're dealing with fluids, you have the equivalent to the simple supported beam. Is you throw in a sphere in water and you have to compute the speed to which this falls. And this is a very complex problem. You can see that it requires moving the mesh, and even the simplest problem, sometimes we cannot solve because we don't have this technology. And you obtain beautiful pictures, but at the end you have to compute. There is an analytical solution for that. And then this you apply to problems that the Naval Architect School do as everyday practice. They take a model of a boat, they put it in the canal, and then they pull it, they drag it, and they compute the forces. And with these forces, they compute the wave pattern, and they compute the resistance of the boat. Again, beautiful pictures, but this is the main result. Is the so-called drag resistance to fruit number. And this is the curve that is used to design the ships. We have to learn this, and this curve you can obtain by experiments, and then projecting to real scale, or by the virtual towing tank, and apply to the design of merchant ships, or other ships not so nice, like this frigate. And here comes a problem. If you are given this data, how long will it take you to create the data for the analysis? And for that, we have developed our own pre and post processors that you can freely use. And this helps us to clean this complex geometry and to produce an analysis geometry like this one, from which we can actually do the computations. So using and obtain the results, or do the structural analysis, which is like computing a building. These are examples of the virtual towing tank applied to this problem of this other one. This is an area of much interest now because of the for the global climate and the ice routes in the Arctic. And of course, if you don't like frigates or you don't like merchant ships, you can do sport boats like this American Cup boat that we analyze. We analyze the underwater behavior, and we compute at the end these curves, which is the drag, the forces in the longitudinal and transverse direction, which are used to design the boat. But of course, you have to also to look to the sails. And the sails brings another element, which is air, not water, air. You have the virtual air tunnel. You use it for one or two sails. You obtain the patterns of the wind and the forces. And the forces in the wind, in the sails, and the forces in the boat helps you to design the ship. You can see here. Okay, so this is just. And our students today can use these tools for these final year projects. This is an MSc project. Okay, this student was from Imperial College, And they use it to clean the geometry, to put it into the tunnel, into the virtual wind tunnel. Well, this is I borrow in this presentation from his final year project, thesis project, master project. Okay, so not huge measures. They compute the air fill and the pressures and results. So these are 20 years ago. This was very hard. Now this can be done. In La Palma, there is a volcano now. You have heard there is a volcano going in La Palma, which is a terrible situation. And La Palma is also one of the largest observatory of the sky in the world. And this was a large telescope. This is in a mountain, which is in the other part of the island. It's called Roque de los Muchachos. And here there is this telescope that has 10 meters diameter mirror. Okay, so the mirror has 10 meters diameters. So it's quite big. It has to be built on segments. And we analyze the air dynamics of the structures, how the wind will move inside the structure, so that will not pollute the vision at night. And I tell you, you could have the best program, fluid mechanics problems in the world, you can have the best theory, but here is a problem of data management, is the D, data management. You have to manage the data from the telescope. You have to transfer this data to the mesh generator. So the management of the pre and the post is more important than the actual sometimes, or equally important than the result. For instance, this is transverse cut over a tetrahedral mesh. You know that in air dynamics, the structure is a boundary condition. The air flows in the mesh that you create, and the structure is a boundary condition for the air. Okay? And you can see here how the air is moving inside the structure, and you compute the time that the particle takes inside the telescope, etc., etc. So this is an interesting problem. And more than that, because the astronomical community is making sure that they're going to have work for the next 200 years. Why? This was a 10-meter diameter telescope. Now in Europe, they are pushing the 50 meters telescope. 50 meters, still they don't know when this will be built. Probably we will not see it, I don't think. Maybe in 50 years this will be built. The 50 meters, but they already studies, projects going. But there is a group for the 100 meters telescope. So you see, when this will be built, who knows? But there are already pictures of this 100-meter mirror telescope. So you can see that at least we know that this is going on, and we are trying to be part of this project because we will live forever in terms of research interest if you are part of this initiative. Okay, wind. Wind is used now for pollution. In Barcelona, we compute the airflow in the city, and we make sort of studies of how a pollution source will propagate. This is also very trendy, very, this is one priority, and I would like to mention it here. And going back to water, environmental mechanics, we have a group, we have a laboratory, it's called Flumen, that we study the flow of rivers and reservoirs, and this is the study of the flow of a river next to the airport, because the river mouth is at the airport. You see, this is Barcelona airport, this is where the river comes, and what you do here is you do river dynamics. And what do you use for the river dynamics? Well, you use fluid mechanics models based on simplified Navier-Stokes equations for so-called 2.5D shallow water flows. Or a reservoir, you see models of how the reservoir will, if you have a problem with the reservoir, how will invade the land. Or a city, if you have a big flooding in the city, this is near Barcelona, Mataró, how the flooding will affect the city. Well, this is just to mention that different fields where these methods are applied today. For instance, we have even imagined how a tsunami will affect Barcelona. This is just to tell you that, well, my house is in this part of Barcelona, so this was a simple exercise. Tsunamis don't occur in the Mediterranean, they occur in other parts of the world. We are also studying, but this was an exercise to see how this will affect the city. Now, from the sails of the ship, we move to airbags, and then we move to inflatable structures. inflatable structures. And then they are not used only for the kids. We created a spin-off company from ThymNet to exploit these inflatable structures. In this case, was exploited for a museum, an itinerant museum. These are inflatable tubes, low pressure, 0.15 millibars, 0.20 millibars, excuse me, 20 millibars. But now these are examples of another inflatable structure in Barcelona. This is an interesting area. You can see here how this was. But I wanted to mention this other application. Now we see a future for the so-called smart structures you can move around the world, and for uses like this, like inflatable hangars. This one was built in Madrid. These are hangars which are 5 meters diameter tube. So they are quite big ones, and this comes from the technology that we use for the shells. This one is in Saudi Arabia. You can see how this structure that will take months to build is inflated in only 1 day with 8-meter diameter tubes. And here you have to apply aerodynamics for the air forces on the structure, and also structural mechanics concepts for the analysis of these membranes with cables. Okay, so this is a new area that we would like to explore, to explore cooperation with you here in the area. Bridges for emergencies. We are engineers. Light bridges, not steel bridges that were used in the Second World War. These are bridges which are inflatable beam with some cables and a very light slab that you can actually carry even in an helicopter. And we have now produced 30 meters span bridges and 50 meters span bridges. So these are lightweight structures for many applications, but mostly for emergencies that I would like to bring here. To enter into the world of manufacturing process will take a long time. So this is only, you can see here the list of problems that you can do with computational mechanics. I did my MSc, for instance, in sheet metal forming. This was my field in Swansea. But if there is a field where there is a future for quantitative method, is industrial processes, because accuracy is very important. I'm only showing here examples of casting. This is, and here we have very complex geometries. We have to fill with a metal of 1200 degrees. Then there is solidification. So handling of complex geometry is essential, fluid mechanics, and then heat transfer, solidification, and then coupled with structural analysis to compute the strength of the part. Yes, well, let me just move on with this. Metal forming, part that you form by pressing, that you perform a number of applications, that you use very fine meshes, that you compute the safety in terms of breakage. So this is a very hot area, very important area. Deformation of metal parts. To analyze this part, and you predict if it is going to fail or not before you actually manufacture the real problem. Okay, this is another problem. Let me come to the final part of my presentation. Is that I would like to, which is producing waves and impacting on ships, or impacting on the harbors, or impacting on structures like offshore structures. And for that you need a different technology. Of course, this is a fiction picture. This is another fiction picture from a movie, but this is not a fiction picture. This is a picture from the tsunami in Japan. So we have the responsibility to produce a new generation of numerical methods that can solve these classes of problems. And we have developed a new approach that combines techniques from particle methods and finite element methods. This is called PFEM. I'm going to explain it to you without equations. Think that you have a collection of 50 particles, 100 particles, or 100 million particles, and you assume that all the information of the problem is in the particles. For instance, you assign velocities, viscosities, everything is in the particles. Think that you can press no boundaries. When you have a boundary, then you can apply a boundary problem. Then you can solve a differential equation. So we go from the cloud to the domain, and from the domain to a mesh, because we use finite elements. And this is what we call particle finite element method. From the particles to the domain, from the domain to the mesh, and then again, from the domain, we abandon the mesh, and we repeat this process a number of times. This is a very powerful technique that we have developed that introduces computational geometry, because you have to identify from a cloud of points a boundary, and requires advanced mesh generators, but now they are very fast. And with this, actually, you can solve these problems of, for instance, this could be a polymer or a rock. You can see in the first row the particles, the domain, and the mesh. And you can see that as the rock is being excavated, or as the polymer is burning, you are changing the geometry of the problem. This has allowed us to introduce concepts from structural mechanics into fluid mechanics, because we use what is called a Lagrangian formulation. What do you do in Lagrangian methods? You have an initial configuration, you have an actual configuration, and you have the current configuration. So in fluid mechanics, classical fluid mechanics, you use Eulerian approaches, where you look to the domain and you see the flow passing. Here we follow every particle of the fluid. So we are using the equations of structural mechanics to solve the movement of fluids and bodies together. And these are the equations that we are solving. We're solving the equilibrium equation, the one I presented at the beginning, the constitutive equation for the deviatoric stresses and the pressure, and we could also add temperature. So this is nothing that the first equations that I presented at the beginning, but now apply to fluids. We apply boundary conditions. And I introduce here the work of Pavel Rysakov has developed this approach in Barcelona, and so I took the liberty of putting your picture. Pavel, you look a bit younger here. Sorry. And these are results that he has obtained. But quite impressive results of moving bodies in water. Bodies impacting walls, for instance. In this case, I will not tell you the details because I don't want to take. Bodies that you can actually throw into water. Methods that you can use to study the effect of waves on breakwaters, or the effect of waves on moving bodies like a lorry. So by combining concepts of structural mechanics into fluid mechanics using these Lagrangian approaches, you can, in this way of reproducing the domain and the mesh at every time step, you obtain amazing new results. You remember I told you this could be a rock I was excavating? This is how we excavate the domain. And here you can have a soft domain, or you can have a hard domain. You see? And the method is the same, but the difference is in the type of soil you're excavating. For instance, we have applied this to tunneling, to excavate tunnels. You can see here. Think of any other method. No other method could do this easily, combination of these two techniques. So this is a new trend that I really think is in the future. With that, I could use my last 10 minutes, if I can, by telling you a little bit about what is the challenge for the near future. I started slow, I have gone very fast through a number of concepts and methods, but I think you are having a glimpse of what's going on here. What is the challenge now? The challenge is that some of these flows, as you see in the tsunami, have particles inside. No, it's not only fluid. For instance, in food mechanics, you have fluids and you have particles of all kinds. In the pharmaceutical industry, so what you want is to actually be able to deal with particulate flows. Because here you have, in these cargoes, you have grain, you have things moving inside. So you want to model the whole thing. Or if you want to study the ships moving in the Arctic, you need to deal with particles which are the ice particles. Or when you have a dam which is falling, this is my hometown, Valencia, the whole dam was wiped away. You want to see how the dam is flowing in this catastrophe with the particulate flows. Environmental problems involve always flows which contain particles. Sometimes the particles are very small rocks, or sometimes it's a cow or a car. Not to mention all these other events that you know that involve particles and fluids. Particles and fluids. Anyway, I don't need to insist on the importance of this problem. And here what we are doing, we introduce the PFM with particles and the fluids. So how do you do that? Very easy, not quite easy, I said. Coming from structural mechanics, well, in the oil and gas industry, we are working here. This will be another lecture, how we produce the particles 6 kilometers under the ground, and we take them to the surface in these small tubes. They are transported by a fluid, is bentonite. The number of problems in particle flows is greater than in structural mechanics. Believe me. There is an industry behind. You will be surprised. We have a conference on this topic. It's called particle methods, and I am more and more surprised. So we have to develop methods to deal with particles. And there is a method called the discrete element method. I don't have time to explain it, because you need to know how these particles interact, and then you have to put them in a fluid. In the discrete element method, there are two classes of problems. The non-cohesive or the cohesive. Okay? This is non-cohesive. Yeah? And the discrete element method is governed by the interactions of the particles. I didn't mention, but this is very simple. The equations are Newton's law applied to the forces between the particles. And the particles could have any shape. And then you have the cohesive particles. To introduce the cohesive forces, there is a community of people who are dealing with the equations between the tangential and normal forces in particles, then they don't know anything about differential equations. So this is a completely different community, and we have learned this, and we have developed methods to model discrete element method. And what we are doing now, we are blending the discrete element method with the finite element method. What do you mean? Well, we have a mesh of finite elements, and when we see that the fracture is initiating, we put discrete elements. And this is what you get. This is what you get. So, because think, for instance, you have a big wave, it impacts against a wall. How are we going to break it? How are you going to break it? Well, this is a method that we use. A tunnel. You have here the front of a tunnel, and you have explosions. And this is a finite element mesh, and when it breaks, the elements break, we introduce these discrete elements. You see? It's the blending of elements. It's like the blending of cultures. This is what we are seeing in Europe. You have a method that comes from outside, and we introduce it to do things that we could not do before. You see? We have to... these problems cannot be solved only with one method. Well, this is another case. I will skip it. For instance, we are breaking all our Romanic churches. You see? We have an earthquake, and if you have an earthquake, all the old churches break down because they don't have any reinforcement. This is another church that we are breaking. So this is an exercise. It has no interest. It's only to see how the method can be applied. But what is very interesting now is you put all these things together. You have the fluids with the PFM, you have the particles, and then you have the possibility to break walls. I don't think I'm going to take much more of your time. I think I will give you the presentation, and I will move to the last part, because this is a bit too long now. So perhaps I will show you maybe a couple of pictures. This is cereals in a glass of milk. Let me just put. This is the rest of the you see? This is what I mean. You see, you have a slope, you have the flow with the PFM, you have the wall falling, you have the car falling. You can move rocks. You can do landslides, but landslides over reservoirs. So you have the ground falling. This is the Bayonne landslide. You can actually bring the mountain inside the reservoir, and there is the flow mixing of water particles. And now you can do this. You see? So this is a very promising trend. And the message is simple: blending methods, fun elements with geometry, computational geometry, and then the particles. And the difficult part is in the fun elements, differential equations. People dealing with particles, I tell you, they don't know anything about differential equations, and they survive. So let me just go to the last 5 minutes. Perhaps this is almost, I take 1 more minute to tell you, because this is something that could be of your interest. This is going to be a hot topic, not only from the, I would say, economical, political, but from the engineering point of view, how this icing is going to affect us. Well, we will have ships moving in ice, but ice is going to break, and then you have to introduce the properties of the ice, and you have to design new ships that could be moved in these icy waters. You can see you have the buoyancy effect. This is soft ice, and this is hard ice, and the fracture is different. So these are discrete elements with cohesion, modeling ice, impacting with the ship. Okay, so this is how this is moving. So I wanted to bring this topic because I think it's closer to you than to us. But if you compute the forces. But there is a whole community of biomedical engineering where they study particles. Particles in the air, in lungs, particles in the blood, particles in the heart. So I can tell you, if you choose the field, and then you will find the particles, the fluid, and the structure. The structure could be the wall of the aorta. Well, I will not show you more videos. Well, because what you see is basically the same. Is particles moving, and the mechanics. The pictures are nice, but the mechanics is completely different. Another case here for the design of this valve. Not to mention the structure, but structure I would say is the easy part. It's not easy, but it's the easy part. So this is the conclusion. That combination of methods. But of course, how about everything that I have not said? How about high performance computing? How about artificial intelligence? What does it mean, artificial intelligence? Machine learning, deep learning. How about reduced order modeling? Data-driven computing, quantum computing, Internet of Things, that mean devices that can talk to us. These metamaterials that have unique properties, because you actually design the material and then you manufacture the material using additive technologies. All this in the context of energy sustainability. So you see, this lecture is incomplete from the beginning. I have insisted in what I like, in what I know, I can talk. I have to tell you that we are cooperating with Professor Cesberuskin here from this country in the high performance computing part. Some of you know him. He's a classical participant in our conferences. We have published one of his books. We are working now with, I told you about particles and not differential equations, but this is going even further. With data and no differential equations. We get data from sensors, and from the sensors we compute from data, data-driven computing. We are now trying to use reduced order modeling to understand how billions of particles could be modeled in a single, I would say, reduced neural network, to educate a neural network for these particulate fluids. So in the middle you have the neural network. At one side you have the offline computations to educate the real network. And then from that you will use for the particulate fluids. This is something we are working. We have published a couple of papers. So this is completely new world. And these are some results of this. For sneezing, we have produced a paper on this for the effect of sneezing and humans. Or this is the last paper. This is the last image they gave to me this week. Water vapor from a chimney compete with this method. Anyway, I anticipate a very challenging and promising future for the development and application of numerical methods in engineering for the benefit of humans. It's important, the last sentence. And let me finish with some tribute to the Italian colleagues. They have provided me with this picture of how to use particle methods and computational mechanics for the design of ice creams. Okay, why not? And there is a future there also for many of our engineers. Okay, but of course also for the movie industry. You know, this was an old picture, so I think now it's time for us to refresh and take a glass of water or any other liquid that we can think. With that, I think I would like to finish this presentation. And sorry I took a little bit longer than expected. So thank you very much. This is the end.
Thank you very much, dear professor. Any questions, please, colleague?
May I? Okay. Thank you, Professor Onьяте, for your presentation. I have one question, not about modeling and these methods, but about your university. In one of the first slides, you show you the circle of ideas. And third part is spin-off companies. Do you have in your university or around your university spin-off companies? And how many companies created in your university?
The spin-off companies at the university, there are several. Because there is an organization that creates spin-off companies. In CIMNE, we have created something like 15 spin-off companies. I could, can I use 2 minutes for this? Can I?
Yes, of course.
This is a presentation we did to our local minister. And at the end, so this is our model to create companies. In the early days, CIMNE, our organization, was a partner in some companies we created. In the top part, you can see in blue, there was CIMNE. But it was quite complex. And what we did is we sold one of these companies. It was quite successful. It was an e-learning. And then we invented another model. We created a new company called CIMNE Technology. CIMNE Technology is like St. Petersburg Technology. It's a company owned by CIMNE, 100%. And CIMNE Technology now is the company that creates companies. Okay? So CIMNE Technology is an instrument of CIMNE. And we have created companies in these sectors. In software, software for manufacturing, Quantec, software for naval and marine, Compass. Energy management, helping municipalities to save energy. Take any city in Russia. Who is going to advise the city to save energy? Not the providers. Not the electrical companies, because they want to, they want at the highest they consume, the better, you know. So now there is a new business, for engineers to advise municipalities or large companies, Zara, for instance, to save energy. BData is another company in the energy sector. And then inflatable structures I mentioned. Open science, I would like to discuss this with Professor Baravkov. Open science means how to manage digital documents. But digital documents not only for publications. Have you heard of, now there is a new area which is called building integration modeling. Every new project, a ship, a building, a machine, will be in digital form. Now, how are you going to manage that information? Where are you going to store it? We have created a company for that. Well, and other companies, fresh water, very important. We have a company. So this information is in the web, and I will pass also this information to you. Now, creating a company is is a kind of romantic adventure. You need people who is going to devote to that adventure all their lives. It's very bad when academics do that. They can be the promoters, but you cannot do the two things at the same time. It's very hard. It's very hard. Sometimes you can do it, but 99% you cannot. And it's very difficult to succeed. It's very difficult to succeed. So I only say that. So but I think we have to do it. Why? Because we as a research organization, we need money to pay our students. And the government is only giving us limited amount of money, only 20% of the budget. So how are we going to pay our researchers? So the ideal is that the companies talk about hundreds of millions and we talk about hundreds of papers. This is the dream.
Thank you. Thank you. Any questions, please?
Thank you very much for very interesting presentation. My question concerns the modeling and simulation. And I see some small contradiction. You start from the variational principle for the continuum mechanics. But later, when you speak about the particle, you don't use the variational principle. You directly write the equation at the fourth level. Newton. Why? And you speak about the near future. The next 50 years, we write variational principle or write the Newton mechanics?
No, the variational principle, the continuum mechanics, we will need for the fluid, we will need for the structures, but for the particles, for the aerosols, for the grains, I think they could be treated with these simplified models, because you don't want to model the breakage of the grain. You want to model the impact of the grain on the structure. So I think the future will be the combination of discrete methods, force methods, the dynamic equation of motion, parabolic with continuum mechanics. But continuum mechanics is the object of interest. The object of interest is the structure, is the solid. So I think both. But you need the particle mechanics. How are you going to model 1 million particles?
But we can use the energetical models, the minimum energy for particles.
You could.
Also possible.
You only work with the forces between the particles. You could. It has a variational form. But at the end, you need a particle in 3D is connected with 30 particles around, or 20 particles. You need the forces. So.
Okay.
You could have it in a variational form as well.
Thank you.
Please.
I invite you, any of you who are interested on this, you can write to me, or you can. I will send this presentation to Professor Baravkov, and you can. We have limited resources. I think probably you have a better, we don't need supercomputers for the research. We have our own cluster. It's a cluster that you can buy with, start with 10,000, 20,000, 40,000 euros. We have a small cluster at the center. And for the development of the methods, it is enough. Now, for large-scale applications, you may need to go to the supercomputer center. So this is the strategy. For a research organization, we only go to the supercomputer center when the methods are mature. They have been validated and optimized. So many of these applications have been run in a PC. All the examples, all that you have seen, they have been run in our cluster because they are not so large. They are not so large. Large is to have a whole building and but when you have a complex problem, the modeling part, the data management is more important than the computation. So before you actually can plug the running, you have to work a lot to generate the mesh.
Thank you. Юрий Кириллович, пожалуйста.
Which one? Okay. I'd like to ask one question. In the beginning of your presentation, you show one slide from which follows that we cannot apply a calculation model without test validation. What is the criteria of the test validation during calculation by finite elements or other calculation procedures? When we have to use validation method?
Always. Well, not always.
It's very expensive.
I know. What I mean is that when I show these beautiful pictures, people say, have you validated your model? So
Yes.
we always need, before a method can be applied in practice, you need validation. So we have design validation. So we have sloshing of fluids, dam break flow impacting a structure. So we have a small validation cases for the fluid and interaction with the structures. And we have published papers on the validation. But without this validation, still people think these are only nice pictures. They say, how about accuracy? Well, for the structure, we have the structural slab, and then we are validating the models on beams. Now we have validated the models on new composites. So I think the laboratory will always be needed before. But as you say, when the method is validated, it's like the COVID vaccine. You know, once it has been validated, they can be applied. But we need the validation.
Yes.
But it's expensive, as you say. And also you can only do it in models, not in big models. But for instance, all the ships in the world have been designed in the lab, in small scale models, using this Buckingham theorem, extrapolating, knowing that extrapolation is not correct for nonlinear cases.
I have been working for industrial application for many years. I know it very well.
So thank you very much for the question.
Any questions? Сейчас. Максим есть?
Things go quite slow, you know. Things take time, you know. Take time. I don't know if you refer to how the world is actually trying to get some insight. In Japan, for instance, they have performed a validation test in this canal. They took wave impacting on a wall. Okay, so here you have the wave coming. If you want to break a wall in a lab, how do you do it? Well, you need this big and expensive lab, you see. This is the only place in the world where I have seen that I'm going to spend more time, but I can show you now our simulation and predicts this, you know. This has taken us to get these tools about almost 5 years of development, but now they are ready to use, but still they are very difficult to use in practice. I don't know if you mean the complexity of the problem. The complexity is that the sea is you have to model it with 2.5D, shallow water. But then near to the shore, you need 3 dimensions, and this is still too expensive. Are you referring to this? So we can do this problem, but still we cannot reproduce the tsunami because we cannot model all the houses. We cannot model of. So I think we are quite far still from. We model the houses as rigid bodies, but we model we see. Still, we need to introduce a lot of simplifications to model the real problem. We are at the laboratory. We are at the experimental level. Still, we are starting. So, well, of course. But you see, in Japan, where they suffered the tsunami, they have been able to produce this simple experiment. But this is very difficult because and now we have a reference. We can compare our methods. The next thing will be to do another experiment. You cannot break a house, you cannot break a bridge. But I think in the next 20 years.
Thank you. Коллеги, предлагаю поблагодарить профессора, почетного доктора Санкт-Петербургского политехнического университета, профессора Оньяте, аплодисментами.